Our galaxy might be sitting inside a giant cosmic void. This isn't just a metaphor. There's a working hypothesis, not yet proven but not disproven, that the Milky Way lies within a vast, low-density region known as the KBC void, or the local hole. If that's true, it means we're observing the universe from a very unusual vantage point, and that could mean everything we measure from here might be skewed. When I first came across this idea, it sounded like science fiction. A cosmic hole, and we're inside it? But the deeper I dug, the clearer it became. This hypothesis isn't mere speculation. It's an attempt to solve one of the most stubborn puzzles in modern physics. And that's exactly what we're going to explore now. Let's start with some context. On the grandest scales, the universe doesn't look like stars scattered evenly across space. Instead, it resembles a vast cosmic web. Galaxies line up along long strands called filaments, stretching for hundreds of millions of light years. At the intersections of these strands, you find clusters, nodes, and walls. All matter, every star and galaxy, concentrates in these thin structures. And between these strands lies emptiness, voids, vast, dark regions with an extremely low density of matter. What's striking is that these voids make up the overwhelming majority of the universe's volume. Some estimates say as much as 90%. In simple terms, space is mostly empty. Matter clings to the edges, like foam pressed against the sides of a bathtub. Here's the key idea from the KBC hypothesis. We're not sitting on a wall. Instead, we live inside one of these giant cosmic bubbles, a region where galaxies and matter are far less dense than the universe's average. Sounds strange? Absolutely. But there's a very good reason to take this oddity seriously. That reason is called the Hubble tension, a fundamental mismatch in how we measure the universe's expansion rate. The two best scientific methods give two very different answers. One says the universe is expanding at one speed, the other says it's expanding at another. And this difference isn't a flaw in the instruments. It's not random noise in the data. It's a consistent, repeatable contradiction. Why does this even matter? Because the rate at which the universe expands determines how old we calculate it to be. The faster it expands, the younger the universe appears. One number tells us the universe is about so many billion years old. Another says it's younger, and both rely on impeccable data. We end up with two witnesses, both reliable, both thoroughly tested, both scrutinized by dozens of scientific teams. Yet they give conflicting testimonies. Before chasing exotic explanations, maybe one of them just got it wrong? Let's take a closer look. We'll start with the first witness and break down exactly how they arrived at their number. 380,000 years after the Big Bang, the universe cooled enough for electrons to finally cling to atomic nuclei. Before this, space was opaque. Light got trapped in a hot plasma, like a flashlight beam struggling through thick fog. Then, the fog lifted. Light began to travel freely. This very first light still reaches us today, stretched by the expansion of space into microwaves, cooled down to just 2.7 degrees above absolute zero. We call it the cosmic microwave background radiation. Satellites like the Planck Observatory, launched by the European Space Agency in 2009, detect it. Tiny irregularities in this glow, temperature differences of just a few hundred thousandths of a degree, allow scientists to calculate the early universe's parameters with surgical precision. That includes its expansion rate. The result? 67 kilometers per second per megaparsec. In simpler terms, every 3.26 million light-years of space stretches by 67 kilometers every second. This is a message from the past, ancient yet crystal clear. Now, meet the second witness. Unlike the first, this one deals not with the past, but with the present. Nearby galaxies host Cepheid stars, giant variable stars that pulse with the precision of a metronome. The brighter a Cepheid, the slower its pulse. By measuring the flicker rate, astronomers can calculate its true brightness. Comparing this with what we actually observe reveals the star's distance. This forms the first rung of the cosmic distance ladder. The second rung involves Type 1a supernovae, thermonuclear explosions of white dwarfs. These detonations always happen at the same critical mass, producing identical peak brightness every time. They are the perfect standard candles, visible across billions of light years with a known luminosity from the start. Nobel Prize winner Adam Rees and his team spent years calibrating this chain, from Cepheids to supernovae, and from supernovae to the universe's expansion rate. Their measurement? 73 kilometers per second per megaparsec. 67 versus 73, a 9% difference. Here lies the biggest mystery. 9% might not seem like much. Your phone's thermometer is less accurate. But cosmology isn't weather forecasting. Scientists have tested both methods independently for over 10 years. Errors shrank, instruments improved, calculations were redone from scratch, yet the numbers never aligned. The chance this mismatch is a random fluke? 1 in several million. This isn't noise, it's a signal. So why not just pick one number and move on? Because the expansion rate isn't some abstract constant. It directly shapes the universe's age. A higher rate means a younger cosmos. One number points to one age, the other points to another. Choosing the wrong one means misdating everything, from the birth of the first stars to the evolution of galaxies. 2 flawless methods, 2 incompatible answers. Neither one is wrong.
And here, something more unsettling than just a debate over numbers begins.
If the problem isn't in the measurements, then the problem lies in what we're actually measuring. One hypothesis that might explain this discrepancy suggests that our corner of the universe sits inside a massive region where matter density is unusually low, a zone with fewer galaxies and less matter than average. But this idea remains just a hypothesis, controversial and far from proven. Standard cosmological simulations struggle to recreate voids of this enormous scale. Meanwhile, different sets of observational data offer conflicting estimates, both on the size of this region and how sparse it really is. Some studies detect it clearly, others barely spot it, and still, some doubt it exists at all. The answer seems close, yet every attempt to grasp it reveals another layer of the unknown. Somewhere within that mystery lies a structure whose vastness we are only just beginning to comprehend. This structure has a name. It's called the KBC void, or sometimes the local hole. The hypothesis suggests that the Milky Way isn't just floating in any ordinary patch of space. Instead, it sits inside a massive region where the density of matter drops significantly. In this zone, galaxies, gas, and even dark matter, there's far less of all these compared to the universe's average. And if this turns out to be true, it changes everything we measure from here, right inside this void. But what really throws scientists for a loop is the sheer scale of this thing. Some estimates suggest the KBC void could stretch up to 2 billion light-years across. 2 billion. Our galaxy, the Milky Way, spans about 100,000 light-years in diameter. That means this proposed void is 20,000 times wider than our entire galaxy. Imagine the Milky Way as a coin resting on a table. The KBC void would be the football field that table stands on, and the density of matter inside this void is far lower than the universe's average. Simply put, we might be living in one of the emptiest regions in the observable cosmos. Now, let's add another layer. The Milky Way isn't a lone galaxy drifting aimlessly through empty space. It belongs to the Laniakea supercluster, a colossal structure linking together about 100,000 galaxies. Laniakea is our cosmic neighborhood, our address in the universe. 100,000 galaxies sounds impressive, but even this vast supercluster is just a tiny speck inside a much larger cosmic void, like a small town lost in the middle of a desert stretching beyond the horizon and far beyond. Here's what's curious. This desert isn't a neutral place. Where matter thins out, gravity behaves differently. Galaxies at the edges of the void, where density starts to climb again, pull everything inside toward them. Our local group of galaxies drifts at hundreds of kilometers per second, and it's no accident. It's moving toward more massive structures at the void's boundary. It turns out we're not just inside this region, we're moving through it, and that motion might be distorting everything we see through our telescopes. But to grasp how this cosmic void could be fooling our instruments, we first need to understand a subtle point: the physics of what happens to space where almost nothing exists. Void space isn't just an empty backdrop. It acts like a cosmic pump. Here's how it works. The edges of the void form walls made of clumps of galaxies, strands of dark matter, and superclusters. This is dense, heavy matter, but the center? Almost nothing. Gravity always pulls toward mass, creating a gradient. Denser regions at the void's edges pull more strongly than the sparse center. Everything inside the void, galaxies, gas, clusters, feels a constant tug outward toward those walls. This isn't an explosion or a shove, it's a difference in gravitational pressure. More precisely, a difference in gravitational pull. The outside pulls harder than the inside, so matter slowly, relentlessly drifts from the center to the edges. Our own local group of galaxies is no exception. When we look at the cosmic microwave background, the oldest light in the universe, the Milky Way and its neighboring galaxies are speeding along at hundreds of kilometers per second. But this isn't random motion. They're moving purposefully, drawn toward massive structures at the edge of a vast cosmic void. Imagine standing at the bottom of a shallow funnel, slowly sliding toward its rim. Only this funnel stretches 2 billion light-years across, and slowly means 600 kilometers every second. And this is where the crucial twist comes in. The universe is expanding. This is a vast process. Space itself stretches everywhere, pushing distant galaxies away from us simply because the space between us grows. But along with this overall expansion, there's another motion, something more local. It's the drift toward the edges of a cosmic void. When a telescope looks at a neighboring galaxy and measures how fast it's moving away, it records the combined effect of two movements, the universe's expansion and our own local flow. The instrument can't tell which part of that speed comes from cosmic expansion and which part comes from our own motion inside this enormous bubble. In other words, the speedometer shows the right number, but part of that number isn't the expansion velocity, it's our own speed carried along by the current. Here's a good analogy. Imagine a boat moving down a river. Someone standing on the shore measures how fast it's moving away and records 10 kilometers per hour. But 3 of those 10 come from the river's current itself. The boat's actual speed is 7. Without accounting for the current, the boat's speed appears 30% faster than it really is. Our galaxies are just like those boats, and the gravitational flow inside the cosmic void is the river, a current we haven't fully factored in yet. There's a common misconception here that we need to clear up right away. It seems logical. If a void expands faster than the surrounding space, then dark energy must be stronger inside it. But that's not the case. Dark energy behaves the same everywhere. The real difference lies in what's slowing the expansion down. In dense regions packed with galaxies and dark matter, gravity acts like brakes, slowing the expansion. Inside a void, there's barely any matter, so there's almost nothing to slow the expansion down. Gravity's braking effect weakens. The void expands faster, not because dark energy pushes harder, but because there's less resistance. And the faster it expands, the more matter flows out to the edges, leaving even less inside, and weakening the brakes even more. It's a feedback loop. Voids grow emptier over time. Now, here's the conclusion everything has been building toward. If we account for our local drift within the cosmic void and subtract it from the measured speed at which galaxies are moving apart, the gap between two ways of measuring the Hubble constant, one based on distant supernovae, the other on nearby galaxies, could shrink or even disappear. What we thought was the universe's expansion speed turns out to be local motion. It's not a flaw in our instruments, not new physics. We were simply measuring from a moving train and mistaking passing poles for the wind's velocity. The mystery behind conflicting measurements might finally be solved. But if our position in the universe can distort such a fundamental constant this much, what else is it hiding from us? And what will happen when the void around us grows even deeper? So here's the verdict. Two methods of measuring the Hubble constant don't actually contradict each other. They're measuring different things. One looks at the universe as a whole, through the cosmic microwave background, the light that's traveled for 13 billion years. The other measures what's happening right here, right now, in our local neighborhood. And our local neighborhood is a void, a cosmic void, a place where gravitational pull weakens and space expands just a bit faster than average. It's not a problem with the instruments, not a crisis in physics. It's an address. Our cosmic address matters. Now, let's take a step back and look at the bigger picture. Two forces shape the fate of the universe. Gravity, pulling matter together, holding galaxies in clusters, keeping everything from flying apart. And dark energy, pushing space outward, driving the acceleration of expansion. Right now, dark energy is winning. And the farther we look, the stronger its grip becomes. In a few billion years, the Milky Way and Andromeda will merge into one massive galaxy. Gravity still pulls strongly enough for this, at least on a local scale. But everything else, thousands, even millions of other galaxies, will drift away faster and faster. Eventually, their speed of recession will surpass the speed of light. Not because they're moving through space faster than light, but because the space between us is stretching so much that their light will never reach us. They will fade beyond the cosmic horizon, forever. Hundreds of billions of years from now, the night sky will grow empty. The cosmic microwave background, the faint afterglow of the Big Bang, are key proof that the universe was once hot and dense, will cool to temperatures too low for any instrument to detect. The cosmic microwave background will become indistinguishable from absolute zero. Here's what that means. Imagine a civilization a trillion years from now, somewhere in that lonely, merged galaxy. They'll have telescopes and questions, but they won't find a single trace of the Big Bang. No evidence of other galaxies. No sign of cosmic expansion. Their brightest scientists, using perfect logic on the data they have, will conclude that their galaxy is the entire universe. Static, eternal, alone. And they'll be wrong, but there will be no way for them to find out. Friends, let me add this. We tend to believe knowledge only grows, that each generation knows more than the last. But space works differently. The universe erases its own footprints. The window through which we can glimpse its history slowly closes. How lucky are we to live in a time when the cosmic microwave background is still detectable, other galaxies remain visible, and the evidence for the Big Bang is still within our reach. We don't know. Maybe this is just ordinary. Or maybe we're peering through the final window the universe will ever open.